Hello and welcome back to Codeblaze and continuing on with the series creating voxel chunks in Unity using the job system and burst compiler. So today we are finally be creating the voxel chunks. We'll be implementing the height map generation and the mesh building job, and we've got most of the basics covered. Also, I just want to point out this is the third time I'm recording this video since I kept making some mistakes. So we need to do some fixing before, since there's one mistake that's been in our code since the first video, and that's our blocks array. So if you already figured it out, that's good, but the problem here is each of our block type has the same value, which resulted in like stone block also being an air block, and so all of my boolean comparisons were going wrong. So just fix it. We just need to give each of them a unique value. So 0 will be null block, 1 will be air block, and stone will be 2 block. And after this we can start with today's episode. So I'll create a new directory called chunk, and here we'll add all of our chunk code. So we'll have a mono behavior called chunk, and we'll create the chunk job. So that's our chunk mono behavior, and next we'll create a struct chunk job, and this would obviously extend iJob, and for that we need to implement the missing member. That's the execute method. Okay, so let's get into the chunk code. Close that, and I'll open my notes. Yeah, so the first thing we are going to do is have a reference to our mesh filter as usual, since we need that to render the chunk. And in our awake method we'll get the reference to the mesh filter, get component of type mesh filter, and then in a start method we'll be doing a few things. So I'll just create the skeleton code of it. First thing, we'll be creating the height map, and we'll be populating the blocks array. Next we'll be scheduling the job, and finally updating the mesh. So we'll start with creating the height map, not height map. And to do that we'll be using the polynomial algorithm, and it's pretty simple. You give in an x and z value and it will pop out a y value for you. So for that we will also offset the height map with the current position of this game object, and to do that we'll just get the reference to the position, and that we'll get from transform dot position. And then we'll also create the blocks array, where this will be a new native array of type block. Okay, and it will be the enum block, and I'll be creating chunks of size 16 by 16 by 16. So the blocks array size, I know it's going to be 4096, and the allocator would be temp job, since after the mesh creation I won't be needing the blocks array anymore. If you are creating a proper voxel system in which you want to have interaction with the chunks and saving of chunks and some serialization system, you can use the persistent allocator in those cases, but temp job would be just fine for this case. Now finally we'll be generating the height map. So to do that we'll be using two nested for loops, one running in x till 16, another running in z till 16, and we'll basically be getting the y value here, y, and we need this to be an integer value. So we'll use mathf dot floor to int. Inside this we'll be passing in mathf dot Perlin noise. Now the inputs to the Perlin noise should be float values. If you input integral values, Perlin noise will always return the same result. I'll put a link down below explaining why that happens, but to make sure our inputs are float values, we'll be multiplying it by scale. So before that, we'll be adding in the game object's position as an offset to the x value, which is the iteration of the loop, and we'll be multiplying this by 0.15f. Now you can multiply with any decimal number here, so and this number will act as the scale of your height map, so you can play with it and you will get different results according to that. Next we'll add the z value, position.z plus z, and we'll multiply this also by 0.15. okay, now Perlin noise returns a value between 0 and 1, but we want a value between 0 and 16, so the result of the Perlin noise that we get, we multiply that by 16, so the height of our chunks would be 16. Now this is pretty basic noise algorithm or the type of height gen map we are using. We are not layering multiple height maps or nothing like that. If you want to do that, Sebastian Lang has a great video regarding that, and he goes in depth on how Perlin noise can be implemented in multiple layers. So I'll leave a link down below to that video also, and you can implement that kind of noise if you want. So now that we have a y value, we'll be filling up the chunk up till the y value with stone blocks, and above it would be the air blocks. So for that we need another for loop inside, which will run till y, and in the loop we'll be saying the blocks array, and here we need an index. So the blocks, the way we are having the blocks array is a one-dimensional array, but the block data is actually a three-dimensional data in x, y and z direction. So we basically need a simple function to convert the three-dimensional points to the correct block index in the one-dimensional array, and to do that we'll be implementing a helper function in our block extensions. So we'll call this public static int get block index. We can call it anything we want, and this will take in an int 3 position, and this will basically return position dot x plus position dot z into 16 plus position dot y into 16 into 16. So this basically flattens out a three-dimensional array to a one-dimensional array, so it will be a little bit faster, and we don't need to create nested native arrays, which is kind of bothersome if you ask me. So with this we can call the block extensions dot get block index. We'll pass in a new int 3 here, and we have our x, y and z value. So for x we'll use the outermost loop's x value. Next the y value is this I value, okay, not the y value that we get from the height map, but rather than the I value, which is the iteration number of the loops. And finally the z values. So just keep in mind all these three values are the iteration numbers of the loops, and we'll say this would be the stone block. Okay, so we'll have another similar loop which will run from y instead of 0, and we'll go till 16, and we'll be basically doing the same thing, and instead of stone we'll say we want air. So with this we have our height map generation done. Next thing we need to do is schedule a job, and before that we actually need to create the job. For this I'll open the cube job, because we can actually copy over some stuff like this mesh data structure, since we'll be needing that, or we can reuse the one from cube job. Next we'll want one more struct, public struct corresponding to the chunk data, and this will contain a public native array, of type blocks, and this is the correct block, right? Yeah, and this would be our blocks array. Again, we'll create it as auto property. Okay, and then we'll define the two inputs, which will be public mesh data, not the cube job one, rather this one, and this will be the mesh data. And finally our public chunk data, this will also be an auto property. Okay, so we have our inputs and outputs defined. Basically we'll be reading the chunk data and writing to the mesh data here. So we are going to iterate through all the blocks here. So to do that, again we'll use 3 nested for loops, one in X, one in Z, and one in Y, all going up to 16. And here then we'll start checking the blocks array. So if the current block is an air block, we don't need to do anything. We can basically continue on with the iteration, since there need not be any faces created for the air block. So we'll just put an if statement here, and we'll say chunk data dot blocks, and we'll say block extensions dot get block at index new int3. We have our X, Y, and Z values, and here we'll basically be checking whether it's an empty block. And to do that, you can either equate this directly to the air block, but I like to have some helper methods for this also. So we'll say public static bool is empty, and this will be a proper extension method, so we'll use this syntax here. So this block, okay, so we'll basically return if block equals air. Now if you have any more empty blocks, you can basically chain them with OR here, so this way this method can be reused pretty nicely. And since this is an extension method, we can basically directly call it here. And if this happens, we straight up continue with the iteration. We don't need to do anything. Okay, now if this isn't the case and we are at a opaque block, we need to now check the neighboring blocks to see if any one of them is an empty block. Then we create the face in the corresponding direction. So to do that, we'll have a for loop here running from 0 to 6 corresponding to the 6 directions, and we'll save the direction variable here, which we get from casting I to direction. Okay, and here we'll be doing an if statement here. So we'll have a private method called check, and this will return whether the block at a given position is empty or not. And if check fails, like if it is empty, then we'll be calling the create face function in that direction. So we can get the create face function since we have already implemented that from our cube job. And here we'll basically be calling the create face function in the direction, and the position will be the X, Y, and Z value, X, Y, Z. Okay, so the only thing we need to do now is implement this check function, which is pretty simple. So we'll have a private bool check. This will take in a position, so it will be an int3 position. Okay, and it will return whether this position contains an empty block or not. Now before implementing the check function, we need to get the correct position. So since we are checking the neighboring blocks, we'll need to increment or decrement the corresponding axis depending upon the direction. So to do that, we'll again have a helper function in our block extensions, and I'm going to copy this function since it's nothing complicated, but it's lengthy to type. So what get position direction does is it takes in a direction and an X, Y, and Z value. This can be concatenated into an int3. So depending upon the direction, it will either increment 1 or decrement 1 on the corresponding axis and return it as an int 3. So we get a position in the direction. So it's pretty simple, and you can take a look here and implement this function. So back to our chunk job. In the check function, we'll be calling block extensions dot get position in direction. We have our direction variable up there, and we have our x, y, and z values. Okay, so now we finally need to implement the check function. Now there are a few things that we need to take care here. Since we'll be incrementing the x, y, and z values, they may go out of range. So that's the first thing we are going to check. So if position dot x is greater than equal to 16, or position dot z is greater than equal to 16, or position dot x is less than equal to -1, or position dot z is less than equal to -1, or position dot y is less than equal to -1. So in these cases we return true. Now I've purposely left out position dot y greater than 16, since I only want edge like faces on the edges to be created in the every direction except the up direction, since up direction will mostly have the air blocks. So I don't want this a layer of faces above the chunk. That is not needed. And to tackle that, we'll again have a if statement here, which will state if position dot y is greater than equal to 16, we return false. So with this, all our extreme conditions are checked. Now if we are at a position inside the chunk, we can easily check whether it's an empty block or not. So we'll just do a return statement, chunk data dot blocks dot block extensions dot get position, get block index, and we already have the position, and we basically check whether this is an empty block or not. And with this, we have our check function done, and also our chunk generation code done. So we can schedule the job now. So we'll save the job handle here, job handle. This will be equal to new chunk job, and this will be equal to, we'll say mesh data. This again we can copy from the cube component. We'll say take this mesh data variable here and save it here, and this would be the one from chunk job, though they are the same anyway. So we'll say there's our mesh data, and finally our chunk data, which we can basically create new chunk data here and say the blocks is equal to the blocks array that we have allocated up above. And finally we schedule this, we call schedule on this, and yeah, and with that we need to call the complete method. So I won't be doing that on complete thing that I showed you in the previous video, since technically that's wrong. And if you haven't seen that, do see that videos in which we experiment with the job system. So we'll call the complete method here, and now our job has been completed. So all we need to do is update the mesh, and that code also we have here in the cube job. So we basically copy this and go back to our chunk job, the chunk component, and paste it here and import anything that's missing. And there's one more thing that we need to dispose, that's our blocks array. Again, if you are creating something more permanent, you will probably be using a persistent allocator, so there is no need to call this dispose method here. So with this, everything should work fine, but you never know, since it's already my third time recording this. Let's see if it works or not. Okay, so we'll rename this to chunk and we'll remove the cube script and add the chunk script and save it and press play to see whether it works or not. Can't see anything, right? But the chunk is actually there. So our camera was positioned at the wrong position. So with this we have our voxel chunk generation done. You can see we have the proper bounds. Now if I duplicate this few times and provide it correct, so this would be 16 in X, this would be 16 in Z, and this would be 16, 16. So we basically have 4 instances of the chunk now. And if I play now, we should see 4 chunks created. If I just zoom out, and you can see our height map has also been properly implemented, so we get smooth transitions between the chunks. And if you go inside, only the faces, no hidden faces are there except for the chunk borders, and you can do that. You can actually remove these faces also if you pass the neighboring chunks block data in the jobs, and you can check the neighboring chunks also, but that's a bit complicated since my only focus here is to show you how job system can be used in a practical scenario. And with this we have our chunk generation done. So in the next episode we'll basically be going over how we can add the burst compiler to it, so that will give us a significant performance boost, but it may not be visible here in the editor. But if you are generating a large number of chunks, you are definitely going to get significant performance boost. And to actually use the burst compiler, we'll need to modify our code a little bit, since there is still places in which we are using managed data in our jobs, and to use the burst compiler we need to completely remove them, and we'll be doing that in the next episode. So if you have any suggestions, please leave them down below in the comments, and if you like, do leave a rating and subscribe for the upcoming videos. Thank you. Bye.